All right, I think it's appropriate to give Hattie a little screen time. Maybe she'll be a little happier listening to some math lectures. There she is. So calm. Okay, let's talk more about bifurcations. And to do this, we're actually going to start by, well, first off, I'm going to show you a bifurcation diagram that you may have seen before. Has anyone seen this bifurcation diagram before? It's a bifurcation diagram for the logistic map. We're not going to worry about this, but it's a really interesting bifurcation diagram. As some parameter changes, right? It's like 1 equilibrium, and then 2, and then 4, and then a few more. But yeah, look up the logistic map bifurcation diagram if you're curious about this nonsense. Anyway, that's just a little fun. Because who doesn't like crazy headache-inducing graphs? We're going to start by making a quick disclaimer. We're going to be assuming something kind of for the rest of this whole textbook. We're going to be assuming that when we're looking at one parameter families, we're going to be assuming that we do have these one parameter families of this type with continuous partial derivatives. So partial f, partial mu, and partial f, partial y are continuous. This is something we're going to be assuming for the rest of the section, I think for the rest of the book, for these sorts of functions. All right, I haven't gone through the whole book yet, but I think they're planning on doing that. Just because when you look at bifurcations, you get really weird things when continuity doesn't happen. Really weird things, by the way. This is a really weird thing. We don't want to worry about this right now. So we're going to be assuming some level of niceness, at least for the rest of the section. Okay, and this is going to mean really, really nice things for us in terms of the linearization theorem. You remember the linearization theorem from last section? You don't need to write this down. You've already seen this, right? It said if we have a differential equation that looks like this, and as long as f is continuously differentiable, so we already have that, right? Because we're assuming it. Then we can classify whether something's a source or a sink or some mystery option, depending on the slope of f. The slope of f is not the same as the slope of y, right? This is the slope of y. This is the slope of f. Because when we plotted f, right, we remembered our Calc 1, right? If the slope of f was negative when y was an equilibrium point, again, for autonomous differential equations, we're only looking at autonomous differential equations right now, then if it was negative, f goes from positive to negative, from increasing to decreasing, right? Wait, well, if you're going left to right, it'd be from negative to positive, so it'd be a sink, all right? And vice versa for sources. And then we had some weird situation over here for nodes. So what we're going to do is now we're going to connect that with bifurcations. So let's consider a differential equation, a one param fam, a differential equation dy dt equals f of, and specifically I want to look at f of mu naught. Let's just look at not the whole family for now, one parameter, mu naught. And at y naught, sorry, just at y, okay? Now, if y naught is an equilibrium, oh, Hetty's getting ready to go. If y naught is in equilibrium and f prime of mu naught at y naught is less than 0, we can use a linearization theorem to say what happens, right? This is not new, right? We just, have this little plot of like different values of y, how they affect different values of f of y, right? We know that if y naught is an equilibrium point, then f is 0 right there. That's the whole point of equilibrium points, is that dy dt is 0, so f is 0. And if the derivative of f with respect to y at y naught for a parameter mu naught, that's a bit of a mouthful, is negative, we know that very locally, we don't know what's happening outside, but very locally, y naught is the function's looking like this. Now, if that's the case, and again, that's only true for certain nice functions, if this is the case, then changing mu just a little bit. Remember what continuity means. Continuity means everything's connected, there's no jumps, so a small change in the input means only a small change in the output. So very locally, if we change mu a tiny bit, it really shouldn't change this very much at all. It should only change this also a tiny bit, assuming we have continuity. That's what this is here for. Change mu a little bit, f should only change by a little bit, relatively speaking. So what that means, what that's going to translate to, is that if we have a slightly different mu, right? Let's say we have a mu1 that is pretty close to mu0, then we're all still going to have a sink nearby. All right? And the sink might change a little bit. And that's going to be true, you know, for sources as well. And the point of this, right? Why am I talking about this? Is we're going to use this to find bifurcations. Bifurcations happen when a small change in U has a big qualitative effect. So if there's a source or a sink of this type, in other words, if we're in either one of these situations, a small change in U is not going to have a qualitative effect. The equilibrium will change a little bit, but there will be no qualitative difference in the equilibrium. So if we're guaranteed to have no qualitative change for these situations, and we're looking for bifurcations, what are we going to look at? We're going to look at this, okay? This is the thing where there might be a qualitative change. Even if mu changes a little bit, we might get some crazy things happening. So that's what we're going to do. That's how we're going to find bifurcations. So to find bifurcations, or specifically to find bifurcation values, what we're going to do is we're going to look for an equilibrium and a parameter of U that has the following properties. Specifically, right, we want it to be an equilibrium, and we want it to be a questionable equilibrium, right? What does this say? This says we want it to be an equilibrium, and this says we're in that third category, or third outcome for linearization theorem. So we just need to find when is the function equal to 0, when is the derivative of the function with respect to y equals 0. Again, there's a lot of variables and parameters flying around, but f prime just means you're taking the derivative with respect to the variable, the input variable. All right, so this is what we're going to do. Maybe we'll star it. It'll be a little method. And we're going to use it with an example right now. And it's going to be another one param fam. I need to stop saying that. And it's going to be dy dt is going to be f mu of y, we'll call it, equals y times 1 minus y squared plus mu. So not quite as easy to see what's going on as before. Not quite as obvious where bifurcation might happen. Okay? So what I'm going to ask you first is mu equals 0 a bifurcation value? And the answer is, well, I don't know. Let's figure it out. All right, let's check the equilibria. Let's see if this is true. This is kind of what we need to look for to find bifurcation values. And we'll go from there. So let's check. What are the equilibria at mu equals 0? Well, f mu, or mu is 0, so it's specifically going to be f sub 0 of y is going to be a very nice equation. Oh, we can find the equilibria here, no problem. Right? So equilibria as y equals 0, y equals 1. Y equals 0 and y equals 1 are equilibria. Now let's check that second condition. Is f prime evaluated at those equilibria also equal to 0? So to do that, we're going to take the derivative. Again, you could use the product rule, or you could multiply all this out, up to you. I'm going to simplify a little bit before I take the derivative. That's actually the other dog. Rainy. Stop it. Whew. All right, so let's FOIL this out. All right, this is 1 minus 2y plus y squared. Distribute, it's y minus 2y squared plus y cubed. And we can take the derivative on the next page and check to see whether these are bifurcations. So if that's the function, then the derivative with respect to y is just going to be 1 minus 4y plus 3y squared. Remember our equilibria, we're at y equals 0 and y equals 1. So we're going to check. Rainy. Stop that. Let's check those two values. So f prime at 0 is equal to 1. Okay, so that's still going to be, oh, let's check our linearization theorem. It's positive. It's going to be a source, right? We know it's a source. And specifically, it's not 0, so it's not going to, we don't think that at this equilibrium anyway, anything funny is happening at this parameter value. Again, we should be using the subscripts of 0, right? There's infinitely many functions here. We're looking at the specific function when mu is equal to 0, all right? And then what happens also when mu equals 0 for our other equilibrium when y is 1? That's going to be 1 minus 4 is negative 3 plus 3. Oh, interesting. So maybe we do have some bifurcation shenanigans happening at this y value, at this equilibrium point. So remember what we have here. Oh dear, that is not the grid I'm looking for. All right, what we have here, if we're graphing something, right, and here's our parameter that's changing mu. Here's our equilibria, y. Remember, we have an equilibrium. We're looking at mu equals 0. There's an equilibrium at y equals 0 and y equals 1. And we're saying that when y equals 1, we might have some interesting things. We know y equals 0 is a source. So in our phase line, we know y equals 0 is a source. So we know our phase line is going to look like this. We don't know what's happening with this other part yet. We could check it. We could add to our phase line, find, right? We could find out what is f doing above this, right? If f is positive, we'll be increasing. We'll have a node. If f is negative, y will be decreasing. We'll have a sink. So we'll check really quickly, right? What is f of, oh dear, I hit the wrong button. Really quickly, what is f when mu is 0? So we need to plug in something above 1. It can be anything. We plug in 2. We plug in 2 into this function. We get a positive times a positive is a positive. So dy dt is positive, which means it's increasing. And we do have a node here. All right, it's going to be very common to have nodes at bifurcation values. Yeah, so that's what we have right here. So that's just the phase line. The phase line doesn't prove a bifurcation. A node doesn't prove a bifurcation, but it is going to be helpful for getting us an idea of where we're going. And I'm going to actually look at a second graph here. Okay, and again, this is why labeling your axes is so important, is because we're going to be looking at multiple graphs, and they're going to have multiple values. So now instead of comparing the parameter with the function value, I'm going to compare y with f mu of y. Okay, and we're going to look at different values of mu here. So if mu is equal to 0, we have this function, right? We know what this cubic function looks like. It has zeros at y equals 0 and y equals 1. Y equals 0 and y equals 1 were zeros. And we know that the 0 at y equals 1 has multiplicity 2. It bounces off. We know that it looks like this. Right? All that pre-calc is coming in handy. And we know, again, this is mu equals 0. And we know what happens for different values of mu as well. Because look at our right-hand side. It's just a vertical translation, right? If mu is positive, what do we get? We get something like that. Maybe this is like mu equals 1. If mu is negative, we move things down like so. Maybe this is mu equals negative 1. And we can actually see bifurcations happening with this graph. We can't see exactly where there's a bifurcation, but we can see that there is a bifurcation, right? Because look, when mu is equal to negative 1, there's only one equilibrium. And y goes from negative, or the slope goes from negative to positive. Negative to positive, it's going to be, like the slope is positive. It's going to be a source. Again, always going back to the linearization theorem, right? The slope of that function f is positive, so y is going to be a source. Here, right, we have in the mu equals 0, there are two equilibria. Here is that questionable one, the slope f prime is 0, but here the slope is positive, we know that's a source too. And then here there's only one equilibrium again. So there's going to be potentially multiple bifurcations. Okay, so how do we find whether there are other bifurcation values? To do that, we're going to go back to this nice red star. We're going to try to make sure that we have an equilibrium and that we're in that third situation for the linearization theorem. So we have our function. Oh, I scroll down a little bit, right? And for any mu, right? I'm just going to copy this to a new page so it's a little easier to work with, right? For any mu, f mu of y is going to be that y times 1 minus y squared plus mu. And we're going to want to set this equal to 0 and its derivative equal to 0. So if we look at this derivative with respect to y, what do we get? That's going to be, again, this equals to y. Oh, I may have accidentally erased it. This equaling 0, the derivative with respect to y equaling 0 is going to find those horizontal tangent lines. We need that horizontal tangent line because that's what we're looking for, right? We're looking for when the value is 0 and the tangent line is equal to 0. By doing this, we're going to find the 2 points. We're going to find both of these points. We really only care about the one that we haven't looked at. We already found this bifurcation value. All right. We take the derivative. Again, you could multiply this out or you could use the product rule. It's up to you. Either way, you're going to get this derivative is going to be 1 minus 4y plus 3y squared. And when you factor that, you're going to get two solutions of y equals 1 and y equals a third. All right, if you're looking for when that's equal to 0, which we are. And again, the y value equaling 1, that was that second one that I erased somehow. And then the y equals a third is going to be this value. So we already looked at this, right? This had a bifurcation value of mu equals 0, I believe. Yep. Great. So what about this one? Does this have a bifurcation value? Is there a bifurcation value for this equilibrium? And the answer is going to be yes. Because again, we saw that as we shifted this down, right, remember, as we shifted this down, we have two equilibrium points. And then the two equilibrium points on the left are getting closer and closer together. One equilibrium point. And then if we shifted it down more, there's no equilibrium over there. There's only that equilibrium point on the right. So we know that there's going to be a bifurcation value at this y value. All right, and again, this is y. And this is going to be our f mu of y. Sorry, I erased that. So what mu value is going to let us do this? Let's find it. And the way that we're going to find it is look at this original equation. Let's look at f mu at this y of 1/3. And when we do that, we're going to get 1/3 times 2/3 squared plus mu. And we want this to equal 0. Multiply that all out, you're going to get 4/27 plus mu equals 0. You're going to get that mu has to be negative 4/27. So we have our two bifurcation values. Let me know if you have any questions, and that should be it. Bye-bye.